This incredibly compact tabletop synchrotron machine allows scientists to study all kinds of materials with astonishing precision in time and space, right within their own labs. In short, the smart light machine generates X-rays by the so-called Compton scattering process, in which intense flashes of laser light are bounced off pulses of electrons moving close to the speed of light, turning them into hard X-rays. Let's see what happens step by step. A femtosecond UV laser pulse produces a bunch containing up to 100 million electrons by femtosecond laser photoemission from a tiny spot on a copper cathode. In the first centimeter, inside a 100 kilovolt electron gun, the high-density bunch is accelerated to approximately half the speed of light, while at the same time expanding rapidly in all directions due to Coulomb repulsion. This Coulomb explosion is halted in the lateral direction by a magnetic coil which acts as an electron lens. To enable further acceleration, the explosion in the longitudinal direction has to be stopped as well. This is done using the strong oscillating electric fields inside a 1.5 GHz microwave cavity. In fact, a high-tech version of a microwave oven, which inverts the longitudinal expansion, resulting in self-compression of the bunch while it's flying towards the entrance of the next accelerator. A second magnetic coil focuses the longitudinally contracting bunch in such a way that at the entrance of the accelerator, the original dimensions the bunch had at creation are nearly recreated. At that point, the tiny high-density bunch is picked up by a traveling wave of extremely strong electric fields, propagating at a velocity close to the speed of light, while oscillating at a frequency of 12 GHz inside a highly compact and innovative microwave accelerator structure. The microwave fields sweep the bunch along until it emerges with a velocity of 99.99% of the speed of light, as if it had been accelerated across a voltage of 30 million volts. Protected by relativistic effects, the high-density bunch now retains its compact size while traveling towards the point where it will collide with an intense laser pulse. However, for efficient generation of X-rays, the electron bunch needs to be focused even tighter, requiring a so-called quadrupole magnetic lens. 10 nanoseconds after creation, the electron bunch hits an intense, counter-propagating femtosecond laser pulse in a point where both beams have been focused to a 10-micron spot. Part of the laser photons are scattered in the direction the electron bunch is traveling, producing a highly directional cone-like beam of hard X-rays. The electron bunch, having served its purpose, is deflected sideways with a bending magnet and ends its life in a beam dump. The remaining X-rays can then be focused onto any surface, allowing scientists to obtain highly detailed images of the molecular structure of its materials, as well as a very detailed chemical analysis.